In the last few videos, we've been working on how we can draw the structure of covalent compounds using the Lewis dot structure method. So we've been drawing structures using a certain process, and that process will always get you to a valid structure, but it does not necessarily get you to the best structure for a given molecule. So we need one more piece of the puzzle to help us determine not only just what is valid, but sometimes there are multiple valid structures that you can draw. And to help us figure out which one is the best, we need something known as formal charge. So formal charge is really just a way of keeping track of sort of where your electrons are. It's a bit of a weird concept because it doesn't really have a physical meaning. Formal charge is not an actual physical measurable charge, but it's often referred to as sort of a bookkeeping method is really the best way of thinking about it. For tracking where electrons are. So what formal charge does is it's essentially comparing the typical number of valence electrons for an atom to the number that that atom actually quote-unquote owns, has full ownership of in a molecule. So the reason I'm phrasing this as the number it owns is because it's a little bit different than the way we count for filled valence electrons. Because bonding electrons are shared, neither atom has full ownership of those electrons. So when we're counting for formal charge, we count things a little bit differently. An atom quote unquote owns all of the non-bonding electrons on it. Those aren't being shared. So any lone pairs on an atom are completely owned by that atom. And half of the bonding electrons it has access to. So essentially, we are splitting the bonds in half. We're imagining, let's go back to our super familiar example for water. Our structure for water looks like this. We know that all of the atoms in the structure have a filled valence shell. The hydrogen has access to both electrons in this bond, as well as this hydrogen. The oxygen has its 4 non-bonding electrons, plus it has access to all 4 of the electrons in this bond for a total of 8. But when we're counting for formal charge, what we're doing is imagining the situation where our atoms get a divorce. They split the bonds, they break their bonds, and they split those electrons equally. So we're essentially imagining 1 electron from each bond going to each of these atoms. So when we're counting in the formal charge sense, we would say that this hydrogen only has 1 electron in this structure. This has 1 electron that it sort of contributed to this structure. And this oxygen has a total of 6. It has all 4 of its non-bonding electrons plus 1 from each of the 2 bonds. So counting for formal charge is a little bit different, and that can get kind of confusing. So remember, filled valence shells, we're usually aiming for 8. Obviously, as we've discussed, there are exceptions to that. But for formal charge, we're looking at non-bonding electrons plus the number of bonds, not the number of bonding electrons. Because those are shared, they get split down the middle between the two atoms when we're counting for the purposes of formal charge. So what we're doing in formal charge is comparing how many valence electrons that particular atom usually has. So that's its group number, as we've talked about before. Where did I say? So the typical number of valence electrons is its group number, just like we've been using to find how many electrons are in the molecule. This would be sort of our actual number in the molecule. And these are the two things that we're comparing when we're determining the formal charge of something. So when the typical and the actual are the same, the formal charge is equal to 0. When there are more electrons than typical, there are actually, for terminology the same, more than is typical, your formal charge is going to be negative. You've got extra negatively charged things, so our formal charge becomes negative. When there are actually less than is typical, if you're missing some negatively charged things, that is going to make your formal charge positive. And the actual value of the formal charge is just going to be how many you're off by. So if you have 1 extra, the formal charge is -1. If you have 3 extras, the formal charge is -3. If you are missing 4, your formal charge is +4, so on and so forth. So for the structure of water we drew up here, all of our formal charges are 0. That hydrogen is in group 1, so it usually has 1 electron. It actually has 1 electron in this structure, so the formal charge of both of those is 0. Oxygen is in group 6. It typically has 6. It actually has 6, so formal charge is equal to 0 here as well. So let's look at a couple other examples where our formal charge is not going to be equal to 0. So let's do 2 examples. And why don't you pause here and use the process we've been using for the last several videos to draw the Lewis structures for both of these formulas for SOCl2 and SO42-, using the rules that we've been following so far. So for SOCl2, first thing we always want to do is figure out how many valence electrons are going to be in our structure. So sulfur is in group 6. Oxygen is also in group 6. We have 2 chlorines, and chlorine is in group 7. So 2 times 7 is 14, plus 6 is 20, plus 6 is 26. So we have 26 electrons that we need to place. Following our usual process, the next thing we want to do is identify our central atom and then kind of connect everything up. So in this case, we have 2 unique atoms. There is 1 atom of sulfur and 1 atom of oxygen. So the less electronegative one is the one that is usually going to go in the center, Based on our electronegativity trend, we can determine that sulfur is going to be less electronegative than oxygen because it's lower on the periodic table. So that makes sulfur our central atom. And we can arrange everything else around that. Next step in our process is to fill up the valence shells of our peripheral atoms by adding lone pairs. So we can do that, add 3 lone pairs to each of our peripheral atoms, and then at this point we want to add any remaining electrons to our central atom. So we have currently drawn 24 electrons thus far. There's 8 around each of our peripheral atoms for a total of 24. We're aiming for 26, so the last 2 electrons need to end up on the sulfur atom. So at this point is where we want to check to see if all of our valence shells are filled. Our oxygen has 3 lone pairs, so it has access to these bonding electrons. The chlorines also have 3 lone pairs plus access to a pair of bonding electrons, so all of those have a total of 8 valence electrons. The sulfur atom in the middle here has access to 3 bonds for 6 bonding electrons, plus the lone pair makes 8. So all of the atoms here are filling the octet rule, so this is a valid structure. So at this point, we want to identify our formal charges. Technically, a structure is not complete until all non-zero formal charges have been labeled. So if something's formal charge is 0, you don't have to mark that. It is implied that it is 0 unless it is stated otherwise. But anything that is not 0, you should include that formal charge, or your structure is not really done yet. So to determine our formal charge, we want to identify how many electrons each of these things owns and sort of compare that to the typical number. So I like to imagine chopping all of the bonds in half. 1 electron from each bond goes to each atom, and that's how I'm going to count things up to determine my formal charge. So we already know what's normal for each of these elements. So my 2 chlorines are the same. Our typical number of valence electrons is 7. In this compound, we have 1, 2, 3, 4, 5, 6, plus the bond makes 7. So our actual is also 7. So my formal charge is equal to 0, and that applies to both of the chlorines because their electron distributions or electron arrangements are the same. They each have 3 lone pairs plus a bond, 3 lone pairs plus a bond, so it's going to work out to be the same thing. For my oxygen atom, we know this guy is in group 6, so its typical number of valence electrons is going to be 6. In this, my actual arrangement, I've got 1 from the bond, plus 1, 2, 3, 4, 5, 6 non-bonding electrons for a total of 7. So we've got 1 extra, which means my formal charge is going to be -1. So I indicate that in my structure by putting a little negative sign near that oxygen atom. And the circle is technically optional. It is fairly common practice just to make the formal charge more noticeable, but it's not technically required. So I will always circle my formal charges to make sure that they're visible, especially negative signs sometimes just look like a stray mark on the page. You don't technically have to circle it, but it is fine to do so and is my personal preference to do so. That's how I was taught when I learned formal charges. So the oxygen has a formal charge of -1, so we do need to label that. And then for our sulfur, also in group 6, so my typical is 6. In this compound, I have 1, 2, 3 from the bonding electrons, plus only 1 lone pair for a total of 5. So my actual number of electrons that this has sort of full ownership over is only 5. I'm missing 1, So my formal charge here works out to be +1, and I indicate that with a little plus sign near the sulfur, and again circling it, just optional circling it for clarity. So one thing to note that can be really helpful sometimes is that the sum of your formal charges must equal the charge on the formula. If that is not true, something is wrong. You've either miscalculated your formal charges, which can happen. If the formal charges you've assigned are correct, what that means is you don't have the right number of electrons. So if you aren't representing the correct number of electrons, you're going to come out with a different charge on the species than you should. So here we have +1 and -1 gives us a total of 0. Charge is 0 on this, so that works out. So the formal charges can actually be kind of a nice way to check your work. Once you get the hang of it, determining formal charge is relatively simple after you've done it a few times. So being able to check and be like, okay, my formal charges add up correctly, this is probably a reasonable structure, can be sort of a helpful way to check your work. So why don't you pause here again and see if you can assign formal charges to the structure that you drew for our other example, for SO4 2-, and then we'll go through that whole thing together. So once again, we want to start off by determining how many electrons need to be in our structure. Sulfur is in group 6, oxygen also in group 6, and there's 4 of them. We also have this negative charge, which is going to add 2 extra electrons. So remember that negative charges add extra electrons, positive charges remove electrons. So we've got 5 times 6 is 30 plus 2 is 32 electrons that we need to represent in our structure. Sulfur is the unique atom, so that is easy enough to identify as our central atom, so we can put that in the middle and arrange everything else around it. Next step, as always, is filling up the valence shells of our peripheral atoms. At this point, we've added 32 electrons. We don't have any more, so we're not going to put any extras on our central atom because we've run out. We've hit our target number, can't add any more, or we won't be drawing the right structure anymore. If we look to check that everything's valence shells are filled, we find that they are. Each of our oxygen atoms has 2 bonding electrons plus 6 non-bonding electrons for a total of 8. The sulfur is involved in 4 bonds, which gives it a total of 8 bonding electrons. So everybody's obeying the octet rule here. If we determine our formal charges, we find that each of our oxygen atoms has 1, 2, 3, 4, 5, 6, 7, which is 1 more than the typical valence, so similarly to what we had over here. Each of these oxygens is going to have a formal charge of -1. Our sulfur has no non-bonding electrons, and we consider it to own, quote-unquote, 1 electron from each of its 4 bonds. So it has 4 electrons in the formal charge counting sense, which is 2 less than its typical of 6. So that has a formal charge of +2. Note that either +2 or 2+ is perfectly fine. I don't care which. Again, I was taught to put the number first and the sign after, but it doesn't matter. And different people have different very strong opinions about it. I don't really care. So we find that the sulfur in this structure has a formal charge of +2.